Hi, and welcome again to your chemistry class, Mr. Nice Chemistry. I'm going to do a live stream today. I just want to make this video announcement, but also give you a quick intro in case anything should happen. You can at least have some sort of beginning to the lesson. So, once again, welcome to chemistry. Let's go, dogs. All right, so we're beginning our next unit is after acids and bases, and I know the second video for acids and bases didn't exactly work out. Let's call a spade a spade. The software I use crashed, so that kind of puts me in a tough spot at times, but it's kind of one of those things you just deal with, and that is what it is. So we are going to roll with the punches a little bit, and we'll see how things go. Oops, that was actually pretty interesting. I want to see. Oh, you go this way with it. All right. Cool. I know this is live, so there's that. Anyway, so first day of thermochemistry. Just is this due now? So you can pause, take a look at it, read it, and give it a shot. And I'm sure you had a chance at this point to take a look. So everything you know about heat, temperature, whatever, here's the thought of, is part D, actually. The biggest thought is therm. What do you think the root word therm means? Okay, let's take a look. Oops, let's get to the slides, actually. So heat, this is one of the prefixes, roots words used for thermodynamics, thermochemistry. Thermochemistry is going to be our study of thermodynamics. It's just the study of heat. Therm is the root word for heat, more or less. And so when you talk about thermometer, it's actually kind of a convoluted use of the term therm, the root word therm. Therm would indicate heat, right? But thermometer doesn't measure heat. Thermometer measures the result of heat exchange, of heat, which is energy change. From one place to another, is transferred from a warmer to a cooler object. So as the thermometer receives the warmer or cooler air, or receives air or loses warm air, the mercury or whatever fluid inside responds to that change by either expanding or contracting, and the expansion allows it to rise up that tube, and all good things going on there. So I'm going to get my background back. I might just blur it because it's kind of flashing me around a little bit. So we'll just go with that. Let me crop it too. All right, we're back. So heat, energy transferred from a warmer to cooler object. Pause and write these terms down, especially as you are unfamiliar. Law of conservation of energy is in any chemical process. Energy cannot be created nor destroyed, but it's converted from one form to another, so it's not created nor destroyed. Right? I should rearrange the wording there. Energy is the ability to do heat or do work or produce heat. So an interesting little diddle there. Temperature, of course, not to be confused with heat, is the average kinetic energy of all particles in a system. So as a particle receives energy, it heats up, right? Okay, so it can move faster. As it moves faster, it has higher kinetic energy. And so as things are hot, they move fast, right? So hotter objects actually do move fast. So that moving fast is transmitted. You can say it's transferred along the course of things. Anyway, that, like I said, the actual movement of particles is what temperature measures. So it does a quick, basically the average kinetic energy of all particles bump into the fluid, and it basically measures that. It transmits that, converts that very quickly. Of course, it's a very rudimentary process, so it's not like it's doing a quick calculation. There is a calculation that's based on, but it's not doing the calculation. It has a fluid that's been standardized to the calculation. Okay, so thermochemistry is study of heat or energy of chemical and physical processes. Chemical reactions lose or gain heat. We're going to demonstrate this by marking the units on the reactants or product side of a reaction. So we'll look at chemical reactions, and we'll look at whether they lose or gain heat by listing the energy usage, energy amount on one side of the equation or the other. Substances melt, boil, evaporate, condense. So change of phase changes. And of course, molecules moving faster or slower depending on their energy. This usually leads to a phase change in various circumstances. So let's keep going then. Okay, we're going to check out a heating curve. You can check out this link through the slides. I'm just going to skip straight to the notes part of it because we have it in this part here. Now, here is an energy flow curve that shows that as heat or temperature is heat is applied to an object, a heat source is applied to, let's just say ice in a pot, okay, a cooking pot, right? Ice on a hot plate, ice in a cooking pot on a hot plate. The heat pressing upward on the hot plate on top of the stove, perhaps, and that is going to be temperature increasing of the ice molecules, okay, and that's going to happen over time. So we're going to watch what happens as that temperature increases and some things that occur along the way. We can actually say as time goes along, we can call that energy added, which would be the energies added across the time. The increase in temperature measures the energy change. So it's sort of putting energy against energy, but we'll see this. The phases that we would list on any phase change. Now this particular one actually represents closest to water, but we can see that most phase change diagrams look about like this. And so along from as temperature is changing from A to B and changing from left to right, this would be the phase of matter that an object is in or substance is in. Solid in this case would be A to B, C to D would be liquid, and E to F, you probably could have guessed it, is gas. Above F, you get another phase altogether. It's a supercritical fluid or plasma, essentially. Think about lightning, right? Lightning or a flame itself. You can't grab a flame. You can't grab lightning, right? It almost ceases to be like other matter. But that's a whole other thing we'll talk about later. Bottom line is noticing that as heat heat is added over a period of time, the temperature increases. This is fairly standard understanding. You've seen this before. Okay, of course, at these phases going from solid to liquid, the B to C segment, solid to liquid is melting. From liquid to solid is freezing. Nothing new there. I do have a new term to call it later, but we'll talk about that when we get to it. And then going from D to E and then E to D is vaporizing and boiling is going liquid to gas. I go this way. Liquid to gas this way, and then condensing is the other direction, from gas into liquid. Do you remember what it is called to go from gas or from solid straight into gas? Sublimation. And did you know there's going from gas directly back to solid? Do you know what that is called? It's called deposition, so that's fun to indicate right there. Okay, so this is our generalized, standardized heating curve. And if we were in class, and when we're in class, I'm going to add some more stuff to it and kind of give you some other things that are going on. And we would say that energy is added, and therefore we can measure the heat that is added. I would go back and actually label on here for students here that heat is a special, the heat being added as temperature goes and energy is added across the time here. There's more energy being added as it stands with more contact with the heat source, right? So from A to B, there's heat added. The symbol for heat is Q. From B to C, heat is still continually added. It just changes forms. Liquid, as it's a liquid, it heats up. There's Q added. As it changes phases yet again, Q is added. As it's in the final phase, Q is added. Q is the symbol for heat, is one of the symbols for heat. There's another symbol we'll look at more later. It's called enthalpy, and it's really just an H, which kind of makes sense. It's like H is like the heat and enthalpy. Anyway, they're interchangeable in a certain sense, but Q is more is a specific type of heat. It's a specific heat, or I shouldn't say specific heat. It's a heat that's discussed, that's about to a place or from a place, heat in or heat out of a substance, right? It's more about where the heat is going. It's normally attributed to about where the heat is going. Whereas H, heat, is just generalized. Heat has moved. Okay, we use a charge or a sign to indicate that later on. Okay, so we're gonna cancel that right there, and we're gonna go from there. Okay, next is this video. I'm gonna post the Edmonds video. It was club day this day, so anyway, I will post this video. I want you to pause right now and go watch Mr. Edmonds turn the sing the heat video on thermochemistry. So take a look, pause, take a minute to do that. All right, if you didn't get a chance, make sure you go back and watch that video from Mr. Edmonds. It's a good one. I'm also going to post a second. He has a second video as well. We don't do it in class, but still worth paying attention to. Anyway, demonstration first one is, what is heat? Right, that's the question we're going to answer here. How can you tell if something is hot or cold? Let's do a little demonstration. So what I want you to do first is take your hand and place it to the surface of whatever desk you might be sitting at. Immediately when you touch it, what does it feel like? It feels cold. Well, let me tell you that the feeling of cold is actually not a standalone feeling. It's an indirect feeling. There is no such thing technically as cold feeling. The feeling you're feeling when you feel something, when you think it's cold, is actually heat leaving your hand. The sensibilities of your nerve endings detecting heat leaving your hand is the sensation we call cold. Okay, now take your hand, which should be nice and balanced. But notice after a period of time, does it still feel as cold as the first touch? No, it doesn't feel as cold as the first touch because the heat has left your hand and balanced out that place on the desk. They have traded enough energy. Another interruption, sorry, there from groups, clubs. Anyway, it will normalize out and you'll end up getting the same amount of heat. Let me put it right here. Maybe here. Okay. It's normalizing out, and so it actually feels the same temperature as your hand. They balance temperature. They exchange energy until they are the same. Sort of like an equilibrium. We'll mention that later on. Now take your hand and place it on the back of your neck. And immediately when you touch it, what does your hand feel like? What does your hand feel of your neck? You'd probably say your hand felt warm. The more overwhelming sensation is that your neck felt cool, but your hand feels warm. The warmth of your hand, perhaps you could try it inside a jacket of some sort. Your hand feels the warmth because there's heat entering inside in your sensibility, your sensation, your nerve endings are detecting that heat arriving back in. So just an interesting thing about heat. Heat is energy transfer from a warmer object to a cooler object. Pause if you need to record that definition again. Temperature is the average kinetic energy of all particles in a substance. Those are from earlier slides. I've just replaced a picture there. Pause and take a look if you need to. So, quick organization of ideas. Here's what I want you to do. I want you to try to create on your own. And on one side, you're going to do it on your own. On another side, I might correct it in case it needs to be different. But create a quick graphic organizer that shows relationships between the following thermodynamic related terms. So create just like, put solid, liquid, gas in a box, maybe in order. Put each word in its own separate box next to each other. And that's all direction I want to give you. And then add using arrows in these other couple words, label your graph with these terms. See if you can do it correctly. So pause right there on a piece of notebook paper and try to draw a graphic organizer. Putting a box around solid, a box around liquid, a box around gas. Have them in order from solid, liquid, gas, and then use arrows and those words to label your picture completely. Okay, I'm going to assume that you did that already, and let's go. Here's what yours might look like. Oops. This might be the beginning of it, right? Now, adding those terms to the list might be a little bit more difficult, but essentially, I'm just showing that going from liquid to gas, solid to liquid, I don't have to do an arrow in between. I could just do one curved arrow to go to one curved arrow from solid to liquid and label it melting, and then backwards is freezing, and then liquid to gas, vaporization, and then reverse condensation, sublimation, solid to gas, gas to solids deposition. One way or the other, make yours look like that. Pause and do it now, because here goes the next. Now we're going to add some other terms to it. Now that we got it the right way. If yours did not match the first time, you can flip it over, start over again, and go back to that slide and copy it down. These notes are online. They're in the Google Drive, which are under in the resources section of Google Classwork, which will be I'll make it at the top, and where I'll put the thermochemistry unit stuff this video, it will be the next subset below that. We're going to add energy to this. Increasing energy of the molecules. These are energy of the molecules. Say that to yourself. Energy of the molecules. Increase going from solid to gas. Molecules' energy increases, which means the temperature measured would increase as well because it's based on the energy they contain as an average. And then the other direction, gases to solids, energy decreases in the molecules. So add those arrows to yours as well. Pause if you need to. Then add the following terms, endothermic and exothermic. But real quick, exotherm. Therm means heat. Exo would mean exit, or exit, sorry. And endothermic would mean into, heat into. Okay, so let's add right there. So increasing energy means endothermic. There's energy being absorbed. Exothermic means energy is being released. It's energy going out of. The actual system, you would say, has lost. Which brings up an interesting point to talk about systems and surroundings and universe. So 3 terms, universe in science. We use the word universe to mean all things. All bits of matter, all time, space, matter, everything that is governable, patternable, and studyable. Okay. A system would be something that is your attention's focused on. So my hand earlier was the system with the in contact with surroundings. The table was the surroundings. My desk was the surroundings. The air can also be the surroundings, is oftentimes the case. But the system is the thing we're focusing on. The feeling of my hand was what we were focusing on. So my hand was the system. The table was the surroundings, as was the air that annotated the change, that detected the difference in feeling. All right. Right. And then, so system and surrounding, we're talking about system and surrounding. System is the point of focus. So everything related to it gaining would be a positive number. Everything related to it losing would be a negative number. Although you can just rearrange some words and you can make a word, make it negative or positive values and things like that, just based on how you say a certain phrase. For example, if I said, my hand, the system on the table, my hand, the system, lost heat, so it had negative energy loss. Okay, but the surroundings received it, so I would say the surroundings heat was positive, right? So my negative loss became the positive gain of the surroundings. The system's loss became the surroundings gain. So depending on how you say it, you can get a positive, negative, any which way you want to. Normally our focus will be what is going on with the system. System loses heat, it's negative. Gains, it is positive. So just bear with me. All right, so we're going to get a grapple hold on some of these different things. We're going to take a bird's eye view and we're going to float on to some gas different standings. So take a look at this little catalyst, this thought, and see if you can come up with some thoughts. We're going to continue on further. I want you to look at your slides on your own, get ahead, and I will add the second part of this video later. Of course, watch the live stream, coming soon, coming today. Please don't crash. Okay, good. It didn't crash on me. Let's go. Thanks for your hard work. Let's go, dog.